Welcome to some impressions from the auto calibration using issues and solutions. We're using this calibration rig with two fiducials on two Z levels. As you can see, issues and solutions presents you with a list of calibration steps, and you can even set some parameters on these steps, like here the detection feature diameter. And we're on the first such calibration step, which is the primary calibration, fiducial position and initial camera calibration. And what this does is it performs a pattern of movement over the fiducial to recognize the camera orientation, flip, switches, rotation, and so on, and most importantly the units per pixel resolution of the camera. This is used to get the real scale of the camera, and we can now do this for the secondary fiducial, which is on the higher Z level. Again, adapt the detection diameter and then press accept. It does this same calibration motion pattern on the higher level, so we can get the 3D properties of the camera, such as the focal length, and this is used to be able to set the units per pixel differently depending on Z. What we also need is the Z level of the fiducials, and we do this by probing them using the nozzle tips. Again, when this is set with the machine, we can press accept to perform the actual calibration. We do this again on the higher level, and what we get then is multiple things. On the head we have now the calibration rig set up, automatically set, and on the down looking camera we get our 3D calibration units per pixels, and I'll quickly demonstrate what this achieves. It achieves very precise graphical jogging performance, so you can really jog to a point, and it's really very precise. And the clue of the 3D calibration is that you can go to the higher level, and because the camera also knows the Z coordinate, it can now calculate the correct units per pixels and again do the graphical jogging with precision. You see it even jogs precisely on this elevated level. Okay, the next step is to move the nozzle over the up-looking camera to determine its position automatically and precisely. You only need to do this roughly. Bring it into focus roughly again, and then, like before, press accept. Now, because this is the nozzle that is moving and not the camera, this does also will also rotate the nozzle around to get rid of any runout that the nozzle still has. So this does not replace the nozzle tip calibration. This is another step that is unrelated, but it does cancel out its effects. This also performs an autofocus Z-level calibration, so this will be set perfectly too. These calibrations can not only set the units per pixel perfectly, but it also set any mirroring or flipping flags and camera rotation, so you don't even have to do that. You get your two-dimensional units per pixels, you get the position of the camera precisely, including the Z, and you get the rotation of the transform. The next step is to calibrate backlash compensation. We use axis X as an example. It does various tests on this axis, moves the camera around to test the x-axis in this instance. And the first thing is a step test, where the micro steps or whatever you have on your machine is tested for accuracy. You see the result at the end, and this goes over 1 millimeter. Then the next thing is a slow approach from each side, measures the backlash with slow approaches, and it does so at different distances to see whether backlash is dependent on distance. And it does the same thing with a fast approach, and it measures overshoot with a fast approach, where the backlash is actually reversed by the momentum of the moving head, perhaps. Again, various distances. This takes quite some time on the real machine. I shortened it down a bit. Now the final test is to actually calibrate the backlash and try different final approach speeds. See speed factor in the indication here. When everything is ready, it uses a heuristics to propose a good method and the settings. Obviously this is also stored on the axis itself, and on the axis we have elaborate graphical diagnostics as well. On top you see the accuracy test that we've first seen and the various backlash results at different speeds or distances. The next thing is to calibrate precise camera to nozzle offsets, and you can do this using a simple paper object. Just take the confetti from a hole punch. It has to be circular, obviously, and again you have to set the feature diameter before you press accept on the solution. The calibration then takes place, and it uses a simple principle to lift up the paper object and turn it around by 180 degrees. And by the displacement it observes, it can determine the true axis of the nozzle. It does this at various pick and place angles to improve the accuracy and to cancel out any angular effects. Note that the runout that you might have on the nozzle or the nozzle tip is equally cancelled out. Usually the nozzle tip is not yet calibrated when you do this nozzle to camera offset calibration, so it's important it is cancelled out by the calibration algorithm. As a result we get the precise detected nozzle head offset. We also see the previous offset and the difference. That's it for now, thanks for watching.